Okay, now we get into the good part. Here's the good part of Chapter 5 when we talk about electron configurations. So we had kind of ended the last time talking about the quantum mechanical model. And the quantum mechanical model says that electrons are not only found in energy levels, but there's also sublevels to those energy levels. And there's also orbitals that exist in those sublevels. And we said that there could be electrons that are existing in the orbitals, which are found in the sublevels, which are found in the energy levels. And we came up with all these different orbitals, right? Like the 1s has one orbital, and the 2s has one orbital, but the 2p has three orbitals. And we remember that s's always have one orbital, p's always have three, d's always have five, f's always have seven. Okay, and so what we have essentially done here is we've set up a map, right? All of the different places electrons could be in an atom, we have set up here. And what we're going to do is we're going to basically draw out or write out these maps for every element. Now, we're not going to do all the elements, but you should be able to do the elements after we go through this. And I always think of this electron configuration as kind of like a game, right? If you're going to play a game, and you guys have played lots of games in your life, if you're going to play a game, every single game ever has two things in common, right? It has two things in common. One, they all have playing surfaces of some kind. Okay, I want you to think about it. If you're playing a board game, obviously you have a board that you have to play on, right? If you're playing a sport, which is a game, of course, you always have a playing field or a court or something that you're playing on, right? If you're playing a video game, your video game has an area that you play within, right? It isn't infinite. You just can't keep going and going and going. There's a certain area that you play in. Well, this is no different. This is our playing surface right here. The energy levels, the sublevels, the orbitals, this is all the areas where electrons can be. The other thing that all games have are rules. Okay? So all games have rules. And so the other thing that we have to do today is go through the rules. The good news about this game is the rules are really short. There's only 3 rules. Not too many games where you could say that. And one other thing before we get started with this is I want you to realize that most games seem complicated before you ever play them, right? If you've never seen a game, the certain game before, like for instance, Monopoly. You probably played Monopoly before. Even if you haven't, you've heard of it. You probably have some idea of it. If somebody brought Monopoly out to you and you had never ever heard of it or seen of it before, and all they did is they took out the rule book out of Monopoly and started reading the rules to you, you would think it was pretty complicated and wouldn't understand it probably right away. But if you played it once or twice, it's not that bad. Right? Yeah, there's a lot of things to learn, but you get the hang of it pretty quickly. Or if you had to learn about all of the rules that are in football or basketball or soccer or whatever. I mean, there's a lot of rules there, but once you play it a couple of times, it's not that bad. This is the same thing. And these are only 3 rules. So you should pick up on it pretty quickly. Now, I also remember the last time we were talking about how do you figure out how many electrons can fit in an entire energy level, and we came up with this really quick shortcut. Again, it's not a big deal, but just remember that it's a possibility that you could do it that way. Okay, so now let's talk about electron configurations. All of the rules of electron configurations are based on one natural law, scientific law. And this law says that everything in nature wants to be at the lowest energy possible. Because lowest energy possible means the most stable. Things that are high energy are unstable. Well, electrons are no different. All right, electrons want to be stable. They're going to be in their lowest energy positions they can be. So just keep that in mind when we're talking about where are electrons going to go in that map that we created. So, electron configurations, the rules. Here we go. Rule number 1, and each of these rules has a name based on the person who came up with it. This one's called the Aufbau principle. The Aufbau principle says electrons enter orbitals of lowest energy first. Well, duh, we just talked about that, right? The lowest energy first is what all things want to be in. So the question is, where are the lowest energy orbitals, right? What are the lowest energy orbitals that there are? So we're going to go through the order of the orbitals and what's lowest energy to what's highest energy. Now here's what I want you to do on your paper, because of course you're taking notes. By the way, while you're out, doing all this, we need to have a periodic table out in front of us too, because we're going to be looking at different elements when we start doing examples here. All right, so on your paper, here's what I want you to do. I want you to list all of the sublevels that we just learned about. And I want you to list them just like this. So you notice I have all of the S's all lined up. I have all of the P's lined up. I have all the D's lined up. I have all of the F's lined up. Okay, so the first energy level only has an S. That's why we only have an S down here. The second energy level has an S and a P. The third energy level has an S, P, and a D. The fourth energy level has S, P, D, F, and so does fifth, sixth, and seventh. So set it up like this. If you have to pause, that's fine, because I'm going to keep talking, and if I talk too fast and you're not done writing, I want you to pause and then come back to this, okay? Okay, so you've got this whole thing written down on your paper. Now, if you imagine that the nucleus, and I'm going to draw this in here for a second. If you imagine that the nucleus is right here. So here's my nucleus of my atom. Remember, electrons are negative, so they're attracted to the nucleus. So the lowest energy place to be would be closest to the nucleus. So if you imagine, you can almost imagine this like a stadium or a theater or something like that, and this is the stage. Well, usually if you go to a concert, the place that you would want to be is closest to the stage. Well, electrons are no different. So electrons would want to go to the 1s sublevel and fill that up first, right? Because that's the lowest energy place to be. But we also learned that each orbital can only hold 2 electrons. So once the 1s is filled with 2 electrons, it's filled. So what would the next lowest energy place to be? Well, it looks like it should be in the 2s and the 2p, right? Those would be the next lowest because those are the next closest to the nucleus. And then we'd fill the 3s and the 4s and the 5s. Well, that doesn't seem so hard. Ah, but here's the key. Here's the trick to it. Okay? It turns out that the nucleus is actually like right here. Okay? So if the nucleus is right there, now what's the best place to be? Right? Well, the 1s is still really close. So that seems to make sense still. We'll start there. Once it's filled with electrons, the electrons would have to start filling the 2s and the 2p. That makes sense. And the 3s is still relatively close. It seems like a good seat to be in. So does the 3p. But now, what's better? This 3D way over here or this 4s? Doesn't it seem like the 4s would be a better seat for the stage right here? This would be lowest energy. And that's what it turns out to be. It turns out that the 4s is actually a lower energy than the 3D. So you'd fill up the 4s first, and then you'd go fill the 3D. And you notice that we almost have this sort of diagonal pattern starting to develop. And so let me get rid of this drawing on here. Okay. And then let's do it this way. Let's say, okay, I'm going to fill the 1s first. So if I fill the 1s first, I'm going to draw this arrow to show I'm going to fill the 1s. Once the 1s is filled, then I'm going to fill the 2s. Once the 2s is filled up with electrons, then the next lowest energy would be the 2p, and then the 3s. What comes after the 3s? Well, we're going to come back to the 3p. But then, like we said, the 4s seems to be a better place, a lower energy sublevel to be in. Once you fill the 4s, look at our pattern here. Now we're going to go back down to the 3d. Then the 3d is going to get filled. Then the 4p. Then the 5s. Then the 4d. Then the 5p. Then the 6s. Then the 4f. Then the 5d, 6p. And this is the order that we would go in. So if you are filling all of these sublevels with electrons, you're always going to start at the 1s. 1s is always the lowest energy place to start. Every single atom has its 1s starting to be filled. If it has more than 2 electrons, then obviously it's going to be done with its 1s and it's going to have to fill the 2s. And if the 2s gets filled with electrons, then it's going to have to start filling its 2p, then it's going to have to start filling its 3s, and so on and so forth. This is the order. You need to know this order. And by heart, you need to know this order. In fact, some people, when they get to the test, the first thing they do is they take, on the test, they would write down this diagram. Okay? Sometimes they call this the Aufbau diagram, because they want to remember what the order is. We're eventually going to learn a little trick that will make this a little bit easier, but you need to know this. This is going to be really important. Okay, so that's the first rule. It tells you what order to go in. Okay, second rule. The second rule we've actually already learned about. It's called the Pauli exclusion principle. And it says that you can only fit 2 electrons into any one orbital at a time. We had talked about that the other day. So 2 electrons can fit into one orbital at a time. Now, why only 2? Well, remember, electrons are negative. They repel each other. And electrons also spin. So if you have an electron spinning, let's say, clockwise, then the other electron is going to want to spin counterclockwise. What other spins are there? There's only clockwise and counterclockwise. There's only 2 spins. So there's only 2 electrons that can fit in there. And then the third rule, the last rule, is called Hund's rule. Right? And it says if you're filling orbitals that are at the same energy, each orbital must be filled with 1 electron before they can fill with a second electron. I always call rule number 3, I always call it the Thanksgiving rule. So we're getting somewhat close to Thanksgiving eventually here. And I want you to picture you're at Thanksgiving dinner with a whole bunch of people. Maybe they're all family, maybe they're all friends, but you probably have a lot of people, let's say, at a Thanksgiving dinner. And you're all sitting down to this big table, and you've got all of these wonderful foods to eat. And one of the foods is mashed potatoes. And it turns out the mashed potatoes are one of your favorite things in the world, and you love them, right? And so people are passing different dishes around the table so that they can take a little bit and put it on their plate. And when the mashed potatoes get to you, you basically empty the entire bowl of them onto your plate, right? You love them that much. And then, of course, you pass now the empty bowl next to you, and, Aunt Susie is sitting there, and she looks at you, you took all of the mashed potatoes. I didn't even get one bite of them. Now, that would be rude. No matter what you think of your Aunt Susie, that would be rude, because everybody is supposed to get a chance at getting at least firsts before they get seconds. Now, that's what this rule is all about. This rule is about every orbital in a certain sublevel getting firsts before they get seconds. And I'll show you kind of how that's going to look here in a minute. That's it. Those are the 3 rules. So you need to know the order that the sublevels go in, so you know what order to fill the electrons in. You need to remember that you can only put 2 electrons in an orbital. And you need to remember that if you're filling orbitals of the same energy, that you have to give firsts before you give seconds. That's it. Now, how are we going to do this? How is this going to look? How are we going to draw out electrons in an atom? Right? That might get kind of confusing and conflicting, but we have a really simple way that we're going to do this. Okay? The way that we're going to do this is we're going to draw out orbitals as boxes. So for instance, you can see in my example here, if I wanted to draw out the 1s sublevel, I know an s only has one orbital, so I'm going to draw one box next to it. And then if I want to put electrons in that orbital, I'm going to draw electrons as arrows. And I do that because I need to just remind myself that the electrons are spinning, and so I can show two arrows going in opposite directions because they're spinning in opposite directions. So I don't have to get really fancy and artistic. I don't have to figure out some kind of crazy way to draw out electrons. I'm just going to draw them as arrows. And I'm going to put them in boxes, and the boxes represent orbitals. And I'm going to label each box with what sublevel it is a part of. So let's say that we're doing the 2p. Right? Remember how many orbitals a p has? A p has 3 orbitals. So I'm going to draw 3 boxes next to the 2p. Now let's say that you have 3 electrons to put in these boxes. Well, according to Hund's rule, I'm not going to put 1, 2 in this first box and then the third one in the second box, because that means that he would have gotten seconds before he got firsts. So I would put 1 here, I would put 1 here, and I would put 1 here. What if I then had a 4th electron to put here? Well, now I could go, since all 3 of these all got their first, now I could go back and I could start putting a 2nd electron in each of these if I have more electrons to go. That's what we mean by Hund's rule. Okay? So these diagrams here where we have boxes and arrows, these are called orbital diagrams. So that's what we're going to start with. We're going to start with writing out orbital diagrams because I want you to get used to how to do this. So let's do a couple of examples. Right, we're going to do some really simple examples. Again, you need a periodic table out because I'm going to be referring to things on the periodic table. How do we know how many electrons each of the atoms has? Well, we learned how to do that back in chapter 4. Right? We learned that electrons are the same as the protons, the same as the atomic number, unless there's a charge. And for now, we're not doing any charges. Right? We'll cover that later. So assuming there's no charges, then as long as you know the atomic number, you know the number of electrons. So let's try this with lithium. Lithium is number 3 on the periodic table, right? So that means that it has 3 electrons. So I want to draw out the orbital diagram for the electron configuration of lithium. So where do I start? Every single electron configuration starts at the lowest energy sublevel, which is the 1s, right? So the first thing I'm going to do is I'm going to put 1s, and I'm going to put 1 box with it. Why 1 box? Because s's always have 1 orbital, and a box represents an orbital. How many can I put in an orbital? I can put 2. So I put 2 electrons in the 1s. Now, lithium had 3. So where's the 3rd electron going to go? Well, since the 1s is now filled, that's it, what comes after 1s? So now we go back to our orbital diagram. We say, oh yeah, after 1s comes 2s. And since it's an s, again, I only draw 1 box. How many electrons do I need to put in there? Well, I only have 1 more electron to put anywhere, so put 1 more electron there, and I'm done. So there we go. That's lithium's orbital diagram. It has, its 1s has 2 electrons in it, and its 2s has 1 electron in it. I don't have to keep going because I don't have any more electrons to put anywhere. So that's pretty easy. Let's try this for oxygen. It's a little bit bigger. Oxygen's number 8 in the periodic table. That means it has 8 electrons. So where do we start? We always start at the 1s. Right? The 1s is always the lowest energy place to be. That's where the electrons always want to start. So I start by drawing out my 1s orbital. I put 2 electrons there. All right, there's 2 of my 8. And what comes after 1s? Well, we learned that 2s always comes next. 2s also has 1 orbital, 1 box. So how many can I put in there? Well, I can put 2 more there. What comes after 2s? So now we go back to our orbital diagram. After 2s comes 2p, right? How many orbitals can you have in a p? Well, it'll be 3, right? So my 2p has 3 boxes. Each of those boxes could hold 2. But remember, they all belong to the same sublevel. That means they're all the same energy. So Hund's rule, Thanksgiving rule, says they all get firsts. So I have 2, 4. So I have 4 more to go, all right, to get up to 8. So I'm going to put 1 here. I'm going to put 1 here. I'm going to put 1 here. Where's my 4th one going to go? Well, now that they all have firsts, now I can go back and put it here. Right? So what if I had 9? Where would the next one go? Right here. Right? What if I had 10? Where would the next go? Here. What if I have 11? Well, the 2p would now be done. I'd have to go to my next sublevel, according to my orbital diagram. All right. How are we doing? Does it seem so bad? Right? It doesn't seem so bad. The hardest thing that for everyone every single year, the hardest thing, especially when we're just starting, is to remember what is the order. For right now, you're just going to probably have to keep looking back at that orbital diagram since you don't know it yet. You don't have it memorized yet. You're just going to have to keep looking at it to remember what order we go in as we keep going further and further here. All right, now, we've only done up to oxygen, right? Oxygen was number 8. You can probably imagine that if I started giving you bigger and bigger atoms on the periodic table, and having you do this process of boxes and arrows and boxes and arrows and boxes and arrows, that this would get really, really tedious. You can imagine if I gave you uranium. You see uranium on your periodic table? Yeah, you're going to be looking at the bottom of the periodic table, right? Uranium is number 92. That means it has 92 electrons. So you'd have to keep going and going and going and going and going with this for a long time before you get all 92 filled in as to where they would be. While you should be able to do that, I don't want you to have to do that because that would be a lot of work, right? That's not really fair. So there is a shorter, simpler way of writing out electron configurations that doesn't involve boxes and arrows. Right? It's called electron configuration notation. And it simply is going to take the boxes and the arrows out of this, and we're going to replace them with just numbers. So, for example, lithium. If you remember, lithium had a box with 2 arrows above the 1s, and it had a box with 1 arrow above the 2s. Well, let's get rid of the boxes and the arrows, and let's just simply write the number of electrons that was in the box. Let's just write that as a superscript. These are not exponents. We are currently not doing any math here. Even though we're using numbers, we're not doing any math. This is not squared. Just because the 2 is written above like a superscript doesn't mean that it's an exponent. So please don't pronounce it that way when you say it either. This would be written and pronounced as 1 as 2, 2 as 1. So there's 2 electrons in the 1s, and there's 1 electron in the 2s, with a total of 3 electrons, which is what lithium had. This is a lot shorter and easier than having to write out boxes and arrows, right? So what would oxygens be? Remember, oxygen had a 1s with 2 arrows in it, then it had a 2s with 2 arrows in it, and then it had 2p that had 3 boxes. But if you count up all the arrows in all those boxes, it totals up to 4. So we have 1s, 2, 2s, 2, 2p, 4. This just makes it a little bit quicker because we don't have to keep writing out all of the boxes and arrows. We can just simply write out how many electrons would have been in those boxes if we had drawn boxes. All right, so this is your chance to try this out. This is where I want you to attempt to do some of these. Okay, you've just seen me do lithium and oxygen. Now I want you to do helium and magnesium. Same thing. I want you to do the orbital diagram. That's the one with the boxes and the arrows. And then I want you to try to write it out in electron configuration notation with the superscripts. Okay? So do it for helium and magnesium on your paper right now. Pause this. Try it out. See, again, you have to learn how to do this. If you just simply watch me do it the whole time and you never try it for yourself, you're going to get really confused at some point. So go and try this and then come back. Okay. So you've done this on your own, right? All right. Here's what they should have looked like. Helium. If you look up helium on the periodic table, it's number 2 on the periodic table, which means it only has 2 electrons. So this one should have been really easy. Where do we start? We start at the 1s. How many electrons can you fit in the 1s? 2. Which means that's all you needed, right? So there's the orbital diagram for helium. That's it. And then if you were to write that out in configuration notation, you just written 1s2. So helium was really short and simple and easy. Magnesium is a little bit bigger, right? Magnesium is number 12 on the periodic table. So it has 12 electrons that you have to show where they go. So we start with the 1s. The 1s would have had 2 in it. And then we go to the 2s next, and it would have had 2. And then what comes after 2s? 2p, which remember 2p has 3 orbitals to it. Now, we would have started by putting 1 here, 1 here, 1 here. But let's see, that's 2, 4, 6, that's 7 so far out of our 12. So number 8 would have gone here then, number 9 would have gone here, number 10 would have gone here. Well, we're not done yet, so what comes after 2p? After 2p comes 3s. Again, it's an s. S's only have 1 orbital. You only draw 1 box for an s. How many can I fit in there? I can fit 2 more. That makes 12. So, if you write this out in configuration notation, it would be 1s, 2, 2s, 2, 2p, 6, 3s, 2. Notice I don't put any spaces in between these. And in fact, if I were to read this off, I wouldn't read it with any pauses either. Magnesium's configuration is 1s2, 2s2, 2p6, 3s2. There we go. This is what I mean by doing electron configurations. We should be able to do this for any element. Like I said, you should be able to do this even for things like uranium. Yes, it would take you a long time to do. I get that. But in terms of how to do it, you should know how to do it. We would just have to keep going, right? What comes after 3s? What comes after that? What comes after that? What comes after that? You have to be able to keep going with this. Okay? Now, one other thing about electron configurations is, like with everything else in life, since there are rules, that means there are exceptions to the rules. Okay? There are exceptions to the rules, and this is no different. It turns out that when we start getting into the really big elements that have D's and F's, and when we start to get to D and F sublevels, turns out the D and F sublevels are much more stable when they're half or fully filled, as opposed to being anything else. Okay? Now this only goes for D and F's, right? Not S's and P's. So, for instance, we know, in fact, I'm going to write this real quick because I want you to be able to see this. Let's say that we were talking about the 3D. Remember, there's 3Ds, there's 4Ds, there's 5Ds, there's 6Ds, there's 7Ds. Let's say that we were talking about the 3D. It doesn't really matter which D we're talking about. Ds have 5 orbitals. So, a D would have 5 boxes if you were drawing an orbital diagram. So, how many could you fit in all 5 boxes? Well, if each box is an orbital that can hold 2, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? So a D could hold a total of 10, which means if a D is holding all 10, it would be really stable. And if D was only holding half of that, 5 of these, it would also be really stable. So that means that a D5 is better than a D4, right? Because D4 wouldn't be half filled yet, but a D5 would be. Now, how many can an F hold? Remember, an F, like the 4F for instance, an F always has 7 orbitals. So it has 7 orbitals, or 7 boxes that would be drawn with it. How many can fit in each box? 2. So how many total is that? That's 14. So if an F had all of these filled, it would have 14 in it. If it had half of these filled, it would have 7. So F7 and F14 are better than any other Fs. They're more stable that way. Right? So for instance, an F14 would be better than an F13. It would be more stable. Now, what does this have to do with when we do electron configurations? Well, here's the exception to the rule then. Here's how things change. Anytime we have an atom that ends its configuration just one electron away from being half or fully filled in its D or an F, then it borrows one of its earlier electrons, usually it borrows from the S orbital right before it, and bumps it up into that D or that F to make it half or fully filled. Okay? That's what we mean by this. So the only way to really kind of see this and understand this is to do an example. So we're going to do this for silver. So here's what I want you to do. I want you to find silver on your periodic table, and I want you to write out the electron configuration notation for silver. Don't write the boxes and the arrows. Don't write the orbital diagram. You're going to take too much time to do that. Right? Let's narrow it down and do just the configuration notation. So like the 1s2, 2s2, 2p6, that deal. Okay? So I want you to figure out what silver's would have been. But don't worry about this exception to the rule stuff. Just write it out as if you were doing it and you didn't know about this exception to the rule. Pause, do that, and then we'll come back. Okay, so you've done silver's configuration, or at least you think you have. Hopefully it's right. So let's go through this. All right, how many electrons does silver have? So what electron or orbital, atomic number, too many words here. What atomic number is silver? On your periodic table, it's number 47, right? So we've got number 47, which means it has 47 electrons. So, following the original rules, you would have put 2 in the 1s, then you would have put 2 in the 2s, and you would have put 6 in the 2p, and then 3 in the 3s, the 2 in the 3s, and then you would have done the 3p and the 4s and the 3d and the 4p, and that's the order you would have gone in. And you would have ended at 4d9. Okay? Now, 4d9 is 1 electron away from being a 4d10, and a d10 would be fully filled. So silver says, you know what? Instead of having to deal with this unstable sublevel here at the end, I'm going to go and I'm going to borrow one of my electrons from the S right before it, and I'm going to bump that electron up and put them here. And so silver's actual configuration looks like this instead. And the only difference, you can see the only difference is, at the end, it decided that its D would be more stable with 1 more electron, which it borrowed from the S right before it. So, this is not a common occurrence. There are not many times that this happens, but it happens just enough that I want you to know about it because it's important that we know what the correct configuration actually is. Okay. The other thing that I want you to realize is this, again, this only happens with D's and F's, so it doesn't work with S's and P's. If you ended up with a P5, you would not go borrow to make it a P6. If you ended up with an S1, well, it wouldn't even matter because S1 is actually half filled. But it doesn't work with S's and P's. It's only D's and F's, and it's only when you're 1 electron away. If this were a D8, I would have not gone and borrowed 2 electrons to make it a D10. It's only when it's 1 electron away from being half or fully filled D or F. That's it. It's the only time this happens. So there's only a handful. Maybe there's like 8 elements in the entire periodic table that this ever happens with. I mean, it really isn't many. Okay. So don't expect it to happen often, but you will see it sometimes. I can tell you right now, you're going to see it on your homework. I can tell you right now that you're probably going to see at least one on the test. Okay. All right. So at this point, you should start to have a pretty good idea of how to do electron configurations. And, by the way, I would expect that now you should be able to do some of your homework on electron configurations. But here's what we're going to find out. We're going to find out that the way that we're doing this, like for instance, this one that we did for silver, takes too long. I don't know about you, but probably it took you somewhere on the matter of minutes to do that. Maybe it took you 3 minutes. It took you 5 minutes to do that configuration because you had to look up what was the order for each of these and how many am I going to have in each, and you had to figure this whole thing out, and it took you a while to do. Well, it turns out that we need to do configurations a lot faster than this. So I'm going to teach you in the next lecture, I'm going to teach you how to do this process much faster. Like, we should be able to figure out what silver's configuration is in a matter of seconds just by looking at the periodic table. All right, so I'm going to show you a trick on how to do this. But like with everything, you got to learn the slow, hard way first. So keep working with this, practice it in your homework. And then the next one, I'll teach you a little bit of a shortcut to do this a little bit quicker. All right?